So then let's begin. Welcome to our course on Fundamentals of Attosecond Science and Technology, or what we call FAST, FAST. And we are presenting this to you from IIT Madras and IIT Tirupati. So now we are in module 2 of this course, which is dedicated to femtosecond laser pulses. And this is the third lecture of this module. We had 2 lectures earlier this week. So today, once again, referring ourselves to these key references, which I'm sharing again because if you can access these texts, nothing like it. They really go hand in hand with the course. And also credits to Professor Trebino for sharing with me his materials and inputs. So in today's lecture, as I did yesterday, which was part lecture, part tutorial, we'll recap a few things which we dealt with in the previous class, and then move into a formal description of pulses and essential recall of Fourier transforms for those who are already adept at it, and for those who may possibly are either out of touch, and I would be surprised if you're not introduced at all to this concept. In either case, it's both. It treat this as a toolbox. You may sometimes want some additional resources for mastering this, in which case I recommend you to look back at your courses, or I am sharing a couple of YouTube links to help you visualize things, because that can be fun. But primarily, any good textbook on engineering math or math physics will give you a very good exercise in Fourier transforms. That said, we are really not going to use more than the tools that I'm going to sort of spell out in this class. I mean, you won't be needing much more than that in terms of dealing with the math in this course. And we'll then go to the frequency domain description of pulses, since we will begin first with the time domain. So recall that we spent quite a while in taking this insight from resonator modes, for which we deduced that the transmission has a spectrum which is like this, where you have the individual resonator, the modes of the resonator, the eigenmodes, the resonant modes, forming peaks with a shape function g of omega, whereas that is modulated overall by an envelope in the spectral domain, which is f of omega. And there is a periodicity in the peak structure of the transmission, especially when written down in terms of frequency or angular frequency, or for that matter, round trip phase. Then this spectrum has the functional form where the line shape function g is convolved with a function which has a periodicity of 2 pi by t, t being the round trip time. Okay, and then this forms this comb of frequencies equally spaced in the frequency domain. But then the amplitude of this entire comb is modulated by f of omega, which is the sort of modulation function which comes out of the physics and specifics of the problem. Now, this being the case in the frequency domain, obviously we can carry this back to the time domain, or so-called do an inverse Fourier transform, in which case what happens is we have a product of two functions. If we know the individual Fourier transforms, in this case the inverse transforms for functions f, g and the periodic function, then and if these are essentially lowercase functions f, g and the periodic function respectively, then the electric field in the time domain essentially, first of all, is a product of is a convolution of two functions. One is little f, the inverse Fourier transform of capital F, and so it's in the conjugate domain, and the second is this entire function. Now, within the second piece of the function, we have a convolution between g and the periodic function. So if I know the inverse Fourier transform of g of omega, and that is g of t, then the convolution here essentially becomes a product in the conjugate domain. So this is essential Fourier transform properties, which I'll also recall more about in this lecture. But the key insight we gained is that this sort of spectral structure for the transmission in the frequency domain and the mode structure results in a finite train of identical pulses being present in this medium. And indeed, as we also understood that the first pulse is emitted in this case at time centered at time t is equal to 0. And essentially, since recall that I in my earlier consideration said that this resonator has no losses, it's a very ideal resonator, ergo it has no gain either. So it's a sort of passive device in that sense. Then if a part of this pulse, part of the energy is stored in the resonator is expelled in the form of emitting one pulse out of the resonator, it could be viewed as such. Then because we are talking about transmittance, then the second one, its intensity would or the peak amplitude would have dropped down and successively to the third and so on, and we could even sort of approximate this to a decaying exponential, right? So this is one sort of realization. Of course, for those of you familiar already with these lasers, you would expect that a laser of this type, which emits pulses, emits a finite train, as even a very long finite train of pulses nearly identical, but whose amplitudes you typically want to maintain constant, which happens in real life. That happens because you're pumping energy into that system, whereas this is not, this device has no gain, there is no amplification. So that's extrapolating our insight even further into what we are going to see soon. Okay, but in this module, our goal is to essentially formally describe pulses or learn to formally describe pulses and in both time and frequency domains. And this is the sort of iconic pulse which we took into account. It's fairly general. It has a Gaussian-like envelope and there is a carrier. And note immediately again that the carrier has a frequency, which the frequency of the carrier going from left to right in the increasing direction of the time axis, the frequency increases because the period actually decreases as we go from left to right. So how do we describe this pulse and write it down in terms of a formal equation? Well, we should once again realize that in writing the electric field down for the propagating wave, recall that we essentially said that there should be, if x is the direction of propagation, then we should essentially have a function which is a function of the form x minus vt, that is x, the spatial coordinate, and t, the time coordinate, combined in this function essentially in the form of x minus vt. But if I fix and observe a point x is equal to something, x is equal to x naught for that matter, and look at the time dependence of this of the field oscillations, then we have in such a case we only the vt part remains. In this case, that's the omega naught t part, although omega naught t here is the angular frequency. Okay, so of course, if that for any reason sounds a little bit, say, strange or whatever, recall that we wrote down electric fields of the form E is equal to E naught exponent of I K dot R minus omega t for the case of an infinite plane wave. So here we fix the, okay, I have the habit of putting vectors and sign underneath my variable, so please bear with that for the moment. So then if I fix this to be one constant value, then at this, at r is equal to r naught, I essentially have I'm writing again a scalar wave. It is like that. Okay, so we are fixing our say attention to one point. By the way, to keep the notation consistent, we are using a subscript 0 or naught to denote the carrier frequency, which is omega naught. Okay, but once again, it's good that we wrote this down again, because now we have we contrast the two expressions, the one for the plane wave here and what we have written here down for the most or a more generic or generalized pulse. We have another function of phase, which is phi of t. So that's a key difference between this ideal harmonic solution to the three-dimensional wave equation for the electric field. If it's three-dimensional, the electric fields here should also have been vectors. They could even be the way we have written, it's complex notation, right? So that goes with it. So there is one key difference here, that phi of t is an additional function which is in the argument of this complex exponent, and we have the amplitude, which is essentially on this view graph. This is the amplitude. So this is captured by the square root of I of t. So there is a fast variation in the phase and the amplitude, which is the carrier, and the slow variation riding on top of it, which is captured by the intensity function. Okay, so this sharply peaked function is what we call the ultra short pulse. We qualified this ultra short better earlier because we realized that within the reasonable measure of width for this pulse, which could perhaps be taken close to about 50% of the maximum amplitude, you have only few cycles of the carrier which are present in this case. So it's indeed a fairly ultra short pulse, because the limit of shortness of the pulse will end at one complete cycle at least, right? So this is fairly short, but but the point, larger point that we want to make here is that the amplitude is written as the square root of a function I of t, which we call the intensity function. Okay, so the envelope is the first part, and the remaining part is all phase factors. Of course, electric fields are real, so we have we take a half of this quantity and add its complex conjugate to it to write this in the form of a real variable. So the phase function here, the phase function of interest, tells us something about how the frequency evolves inside the pulse, and this is something we discussed at length, that if the phase function were to be a constant independent of time, then through the entire pulse the carrier frequency is a constant. But here, if this is not a constant in time, then we can look upon this function in a Taylor expansion sense and say, okay, this is a constant part, first order term in time, a second order, a third order, and so on. All that will tell us how the frequency the carrier frequency varies instantaneously as we walk through the pulse and sweep through it. Okay, so then as a matter of say convenience and keeping easy bookkeeping, let's remove the half and the CC, because anyway the logic is to do all the math and then convert back this entire complex quantity into taking its real part, and that is what matters for the electric field. So drop these as we grow up, and also the fact that the central frequency omega naught is just a number. So it is just going to tell us something about the pulse and the spectrum of the pulse, which we will define soon. So it is we can bookkeep omega naught, that's going to take a certain value. So the essential sort of variation, the important dynamics, if you wish, in this pulse are contained in the defining the envelope, which varies in time, and any further variation inside due to the function phi naught becoming time dependent. So these two capture the essential key aspects. These are the DNA of the pulse, right? So the square root of IT is often called the amplitude or the real amplitude of the pulse. Yes, that's another point that I made and will make subsequently here in it, that I is a real valued function, although the way we have written here, E on the left, which right now we are referring to with a proportionality sign, is essentially can have an imaginary part. It is essentially a complex valued quantity. Now, a typical pulse, what is a typical pulse and an envelope that goes with it? A typical pulse could be having an envelope which is Gaussian. So, for the envelope of the pulse, to a first approximation, which a lot of ultra short pulses can be approximated to, right? We essentially have a description of the pulse through a Gaussian amplitude modulation, where you have the amplitude modulated using the Gaussian function, where t is the time variable and the width is captured in this half width at half maximum, which is t half width at 1 over e. This is also called the half width at half max. It's then related to another popular measure for pulse widths, which is FWHM through the square root of 2 log 2 and so on. Now, correspondingly, if I assume or consider pulses with a Gaussian envelope function, then the intensity as a variation of time, okay, as a function of time, which is again pertaining to the envelope, essentially is again a Gaussian function, whereas the width of the intensity for this Gaussian shape is reduced compared to that of the electric field by a factor of square root of 2. Okay, this is now 4 times the log of 2 in this case. Now, this is a good view of how for the same pulse with a uniform carrier frequency here, right? A uniform constant frequency carrier. We have the amplitude being Gaussian, the electric field envelope function, the electric field real amplitude function is this gray line on which I have highlighted an orange. Okay, I don't know if that really helps, but let's keep it or even remove. The red envelope pertains to the intensity. It's shorter by a factor of square root of 2. Okay, now it's sort of easy to go back between the field description and the intensity and the phase of the pulse. And as a first step towards making expressions more robust, we first of all define the intensity of the pulse formally, I of t, to be the absolute value square of the electric field. The function I of t is the absolute value square of not phi of t, E of t. Okay, so the point here then is that E is a complex valued function. So we realize that E had the function E of t was the envelope and exponent of I something. Okay, the something was omega naught t minus phi of t. The phase is a function of time. Because we define the intensity like this, two things happen. One is the phase factors drop off and we are left with only what was the amplitude, real amplitude of the electromagnetic field. We called it the real amplitude. I've been using the word envelope for it, which perhaps is very appropriate in its description. Right? So earlier we were keeping this as a proportionality, the relation between E and the square root of IT times exponent. But now with this definition, if I define I to be such, the intensity to be this quantity, then essentially the absolute value square of E becomes I of t, and now the rest of it falls in place, and I can easily write down the time dependent electric field in terms of the envelope being square root of IT and the phase factor that goes along with it. So we enforce this equality. So you can argue about the fact that in cases like SI units, we saw, for example, that irradiance, which is a quantity very similar to intensity, was a half epsilon c, the absolute value square of E. So such prefactors can get into this equation in specific if we use particular systems of units. But in this case, we have absorbed them, or we have created some sort of new system where I can do away with such factors and simply use this expression. So what about the real world? Yes, you're going to measure intensity of quantities proportional to it rather than do field measurements directly. So we would be measuring then the intensity in some system of units, and there would obviously be a way to go from intensity to field in each unit of choice that a real world measurement will correspond to. Okay, so now the next, what about the phase itself? The phase function is phi of t, right? And the phi of t, since all information about the wave or the pulse is contained in E of t, taking recourse to the polar representation of complex numbers, the real axis being the horizontal and vertical being the imaginary axis, all we can immediately say is that the electric field essentially has a length like a vector in this plane, which is square root of I of t. And if I focus on any particular instant of time t is equal to ti and ask a question about what the phase of the wave is at that particular instant in time, then it is simply then minus the tan inverse of the imaginary part divided by the real part of the electric field. Why the minus sign? Because our definition contained a negative sign ahead of phi of t. But equivalently, since we wrote down the electric field as the square root of I of t exponent I times the phase function. Obviously, if I now take the logarithm of this expression on either side, I would immediately be able to see that phi of t is minus the imaginary part of the log of E of t, right? So that's another way of writing the phase function. So we can, the essential aim is to sort of correlate intensity to electric field the way we have defined it and rigorously, and the phase function to the electric field. In other words, if I somehow measure the field, right, the full complex, of course you can't measure a complex quantity as such in the real world, but if I have a knowledge of this quantity, I can take out the intensity and phase from it. That's what we are trying to say. Typically to measure, you can measure phases, it's not that we cannot, it's just that to measure phases you would have to have some kind of referencing to another reference oscillator or a reference field, about which we will see and have a lot to say in the remainder of this course as well.